a file for our
BSG.
thing.
Yeah, it's on the BSG group.
It's in the BSG group.
Right. I think I did a debrief of your year 11. So Scott was asking me last week if I were going to talk about the BSG game. And I figured there's a better way of addressing that question because of that particular debrief. In fact, I posted a Word document, which is not as good as the podcast. So I would encourage you to read that podcast about the year 11 debrief because it compares your company's performance in the class and then your class compared against all the SOU MBA cohorts that have played in this particular game since 2000. And then your group also compared against the global teams. And I think in particular, there were two things that podcast talks about in terms of your performance. And while your performance against the SOU teams for year 11, it was better. But in terms of your global competition, you were kind of because maybe it talks about pricing in relation to image rating and then SQ rating. We talk about, and I've heard this many times, that we think about when we try to increase revenue, we increase price. And that's not always good, especially if there's no value added or value proposition when you increase the price. That if to a customer, to a consumer, if there's no additional value to that increase in price, what's going to happen? I mean, this is something also, you can relate this to your game. You increase the price of your shoes, so without increasing the quality.
That price sensitivity versus the quality of
what would happen to your sales?
It drops off.
Drops off, right? So when you increase your price, whether you're rendering a service or you're delivering a product, it has to come with what's in it for me as a customer. All right? I see that at play in my line of work. How many times have we raised your tuition? Right?
You get the board meetings, right?
Whenever, apply it in your business. If you, I don't know, I think Mark talks about this in his MBA 512, that if you increase your price by 5%, you have to understand how much, what erosion in a number of customers, what percent of erosion, so that your increase in revenue brought about by that price increase will offset the reduction in your customer base. Right? I don't know, is that being done in your
in regard to price sensitivity? And I think of it in regards to like price sensitivity.
Of course, yeah. If your product is or service is not price sensitive, or if you are competing in a monopolistic environment, then go ahead, you can increase your price. But if you are providing a service where it's very inelastic in terms of demand, and there are good substitutes out there, be very careful when as your price increase as your first solution to increasing your revenue. Maybe Mark also talked about that in times when sales are declining, a price reduction is even probably a better alternative. Okay, and I think he also showed you a formula how to compute sort of break even, and we will talk about this maybe 3 or 4 weeks when we talk about cost volume analysis. So whenever you make decisions about cost cutting or revenue enhancing actions, always look at both sides. Okay, one of the examples we will look at in quality assurance. In fact, let's do that now. I'm just going to jump right into that. And this will be covered again in that podcast. I think I showed you this graph before. The trade-off between the cost associated with quality and the cost and the benefit associated with spending in quality. So you see that in this graph here, that in terms of level of inspection, the more items you inspect out of a production process or even service processes, that you spend money on inspection. So you see that there is a positive or direct relationship between the level of inspection or the amount of quality assurance that you spend. It will increase, but the benefit will be the cost associated with passing defects, or whether you're talking about defects during the process itself due to waste of material, scraps, or rework. The cost associated with passing defects will drop. Okay, so when we talk about cost of passing defects, you have cost of passing defects during the process and then after the process. And if you're selling products to your customers, your obligation in terms of the cost does not stop when you sell the product. Sometimes you have to replace products that don't last beyond the warranty period. There's a cost associated with harm to the customers when your product, a defective product, causes that harm. So those are the costs that we call as cost of passing defects. Between these two, the cost of inspection appears in your income statement, part of your expenses, perhaps, salaries of folks that are involved in quality assurance. During the process, that the cost of scrap material, lost productivity, those are still easily captured in your income expense statement. But the cost associated with passing defectives after the product is produced, that's a little bit difficult to monetize. You use expected costs or expected values based on the percent of defect that you're going to produce and multiply that by the cost per unit. So as you spend more on quality, the cost associated with passing defects drops. The sum of these two kinds of defects is, when you add, where is my pen? So when you add these two, you have the cost associated with passing defects. This red line or curve is the total cost, various levels of inspection. The cost is the total cost associated with inspection is minimized at a certain level. All right, so that's what we aim for. We want to have a level of inspection at this point where you minimize the cost associated with passing defects. Okay, so let's take a look at that example. Actually, it's towards the end. All right, let's see. Erase my notation there. Okay, so here's the problem. Company is experiencing some financial difficulties. Now they're trying to cut costs. One of the typical areas where organizations typically look at is the elimination of quality assurance. So in this particular scenario, a company currently uses an inspection process in its material receiving the part and is trying to install an overall cost reduction program. Okay? One possible reduction is the elimination of one inspection position. And this position tests materials that has a defective content average on the averaging 0.04 or 4% defect rate that is coming out of that process. Okay. By inspecting all items, they're doing what we call as total inspection. The inspector is able to identify and remove all defects. Okay. The inspector can inspect 50 units per hour. The hourly rate, including fringe benefits for this position, is $9. This is an old example, that's why it's still, the labor cost per hour is still low. If the inspection is eliminated, obviously the defects will go into the product assembly and will have to be replaced later. So this is the replacement cost at a cost of $10 each when they are detected in final product testing. Okay? So, question is, should this inspection station be eliminated? At a glance, so I say, hey, we can save $9 per hour. And that's the cost.
How much does it increase the reject rate?
But there you go. So you look at the benefit. What again? The cost of the hourly cost will appear in your income statement.
4% of 50 is
Two.
and they're $10 each on the return, so that's 20, and he cost $9, so that's how he's worth it.
There you go. So a simple analysis, right? Looking at the percent of defect rate at 50 units per hour, two defects are identified, and they say that that's the sort of the savings that they will have from passing defect, and it costs them $9 per hour for the inspection. So there's a net benefit of $11, right? So I thought, this is the kind of analysis that whenever we look at cost reduction, is we look at both sides of the equation. This morning I was looking at because I part of my one of the things I do in managing. I mentioned this in our first day of our sessions. I manage our enrollment, tracking enrollment, comparing enrollment this year compared to the same period last year. I was looking at the undergrad numbers. In terms of number of seats, students, we are down compared to the same week last year. We're down, I think I wrote it down.
No.
Let me make sure that I have the numbers correct. We are down 14%. Right? The seats translate into, the seats don't really generate tuition revenue for us. It's the SCH, but seats translate into SCH. Kind of scary, right?
Do other people in this room know, other than me, know what SEH means?
Student credit hours.
It's
So
really
you're-
interesting.
You're taking 4. This is a 4 credit hours. So you're paying tuition for those 4.
Yeah.
Okay.
It's interesting when you review the financials of the university because there are certain people on faculty and staff who don't like that we use SCH for
As a-
certain reasons, and then others who do. There are opinions based upon whether or not a department can bring in grant funding.
Well, that's there are multiple.
There's some apples to oranges.
Right. But this one is just like if you're talking about managing the number of courses we offer, you talk about SCH.
Inside one department, it's quite effective.
Correct, yeah, it is. So 14%, really scary. Does that mean that our number of students dropped by that same amount last year? Actually, the number of majors we had, same period last year is the same. So what caused that 14% drop? What do you think?
Perceived value of part based upon the issues in institution of space.
I'm sorry?
I'd say
No, but the number of students that are here is the same as last year.
I would say
So
They're taking less.
probably they're taking less credits because there's less student aid offered, maybe.
it could be, yeah, so yeah, there are areas that you have to investigate and find reasons why that is the case.
Is it possible that the courses got harder and
Not
people
necessarily
don't
the
wanna
course.
take on as much responsibility as the con?
Of course, they typically remain the same year after year.
Resiliency plan did cause some classes to be offered less frequently as well.
Now, in fact, I was looking at the number of classes we offered last year. We offered 49 last year. Because school business, we lost 2.5 positions, which translate into fewer classes for us. We are offering 36 classes this.
Yeah.
So a class is a revenue generator for us. And that happens to be 7 out of 49. That happens to be a 14%,
I have a bit
Decline
of an
number
unfair
four.
advantage for this discussion.
right?
As a board member, I have a bit of an unfair advantage for
Oh,
this.
yeah, and so you are sort of in the thick of things. But the point I'm making here is that when sometimes we only look at one side of the equation and without really looking at sort of the unintended consequences of what we do, right? Same thing here. You can eliminate the position, but we don't realize if we don't do the number crunching, Lawson, right? Lawson?
Yes,
Larson.
Lawson.
Yeah, I do kind of quick analysis and say, what happens if we not offer one extra class this year or next year? That means fewer SEH, right? Especially even if you have the same number of students. So I think we already answered, what is the cost to inspect each unit? That would be, what, $9 divided by 50, right?
18 cents per unit.
Okay, and then the benefit or loss from the current inspection process, we already figured that out as $11 benefit. Okay, and again, if we're looking at financial statements, the cost will show, but the benefits typically will not show. It may show later on. All right, so before we look at the podcast.
Yes.
Okay, so all of these concepts will be addressed in the podcast. Where are you? All right, here goes. And I don't know if I should pause during or let's listen to the whole thing and then we can go back and talk about certain things. Let's do that. Let's just listen to the whole thing and we'll come back, address each one as needed. Okay, start. Hold on.
You just turn the volume all the way down. You have to, on the bottom right, you have to.
No, it's
Because I think it was muted before.
oh,
There you go.
all right. Do it one more time.
So back in 2001, the Ford Motor Company found something like $300 million in just pure unexpected profit, completely hiding in their factories.
Yeah, that's a wild number.
Right. And they didn't invent some revolutionary new vehicle chassis to get it. They didn't slash their workforce in half or anything. And actually, a few years before that, Motorola achieved this massive, I think it was a $1.4 billion reduction in manufacturing costs using the exact same strategy.
It's just staggering when you really think about it.
Exactly. And they didn't do it through marketing. They did it by hunting down this like invisible silent enemy that just bleeds massive corporations dry every single day. And that enemy is called variation. So welcome to the deep dive. I'm your host, and today you and I are going on a mission.
A very math heavy mission, honestly.
Oh, absolutely. We've got this massive stack of presentation slides, technical notes, and research focused on quality control, process capability, and statistical process control. And our goal today, the mission, is to decode the hidden statistical machinery that guarantees the products you buy actually work the way they're supposed to. Whether you're buying a simple box of cereal or a highly complex medical MRI machine.
Right, because I mean, most people hear the phrase quality control, and they immediately picture like an exhausted guy with a clipboard just checking boxes at the end of an assembly line.
Yeah, totally.
But the reality is it's this incredibly high stakes mathematical war. The foundational rule across all our sources today is that every single process, no matter how heavily automated or rigidly structured it is, exhibits some form of variation. It is basically the inescapable background radiation of manufacturing and service.
Okay, let's unpack this. Because before we can fix a broken process, we have to establish what kind of variation is actually breaking it, right? And the slides categorize this into two distinct camps. You have common cause variation, and then you have special cause variation. And they require like entirely different weapons to fight.
They absolutely do, yeah. So common cause variation is inherent to the system itself. I mean, it is the natural, completely unavoidable fluctuation built into the very design of the process.
Okay.
Special cause variation, on the other hand, is an anomaly. It's an assignable factor, meaning a specific localized event that disrupts the normal flow.
I want to ground this for you listening. Think about like my morning commute to the studio. If it takes me somewhere between 20 and 25 minutes, depending on the timing of the traffic lights, that is common cause variation, right? Because the red lights are just an inherent feature of a city grid.
Right, exactly. You can't avoid them.
But if my commute suddenly takes 45 minutes because, I don't know, a cow wandered onto the highway and blocked the fast lane, that is a special cause. It's a completely bizarre outlier.
Which perfectly illustrates how you have to respond to them. Because in a factory setting, the sources mention a special cause being, say, a poorly trained employee filling in on a Tuesday shift and creating these wildly inconsistent parts.
Okay.
So you use statistical process control, SPC, to detect that sudden spike. And then you walk down the floor and you train the worker. You intervene directly.
Right. I follow the logic on the cow and the untrained worker. That makes perfect sense. But looking at the notes on common cause variation, I'm genuinely hung up on something here.
Oh, what is it?
Well, the source mentions this plastic molding process that consistently leaves these tiny flaws, like these little burrs on the molded item. And that is categorized as common variation because it's just how the machine naturally operates. So if it's built into the system, do we just throw up our hands and tell the customer to enjoy their scratched plastic?
What's fascinating here is how the statistical mindset forces a total change in management behavior. Because no, you do not accept the flawed plastic. But yelling at the machine operator won't fix it either because the operator isn't causing it.
Right, the system is.
Exactly. To eliminate those common cause burrs or to shorten your baseline commute time, you cannot intervene at the surface level. You have to fundamentally redesign the system itself. You need to invest in a completely new mold or buy a different machine, or in your case, map out a radically different route to work entirely.
So treating a common cause like a special cause just burns time and money.
Oh, completely. It's useless.
Wow. Okay, so that brings us to how mega corporations actually enforce the system redesign on a massive scale. And that is really where the Six Sigma revolution enters the picture.
Yes. Six Sigma is basically the heavy artillery of process capability. It was originally pioneered by Motorola, and it's a philosophy that just refuses to settle for good enough. To really grasp it, you have to understand the math of a normal distribution, the classic bell curve. The goal of Six Sigma is to squeeze that bell curve so incredibly tight to make the process so insanely consistent that you produce no more than 2 defects for every 1 billion opportunities.
Wait, 2 per billion? That is an almost incomprehensible level of precision.
It really is.
And to get there, obviously these companies don't just guess. They use this super rigid playbook called the DMAIC methodology. DMAIC, define, measure, analyze, improve, control.
Though I have to point out, the presentation deck includes a pretty cynical, but honestly accurate joke acronym for DMAIC.
Oh, right. The dumb managers always ignore their customers joke. I left out that.
Right, because it highlights the most crucial phase of the whole thing, the define phase.
Yeah, the methodology insists you identify what the customer actually values, which the text calls CTQ, critical to quality. I mean, if you spend $10 million improving a feature that the customer doesn't even care about, you haven't improved quality. You just burn capital.
If we connect this to the bigger picture, Six Sigma isn't just about flexing complex math skills.
Yeah.
It's literally an obsession with translating vague customer emotions into cold, actionable data. And you really see this in the analyze phase when they deploy visual tools.
Like the pizza example.
Yeah, exactly. Take the Pareto chart example in the deck, where they analyze the pizza delivery business.
Let's talk about that because a Pareto chart basically uses the 80-20 rule to separate the vital few problems from the trivial many, right? The pizza shop didn't just log that customers were mad, they charted the hard data over 3 months.
Yep.
And the chart shows late deliveries accounting for a massive spike of 1,890 complaints. Meanwhile, the runner-up was wrong order, sitting way down at just 220.
So the data completely dictates the strategy. You immediately stop worrying about, optimizing the pepperoni placement, and you focus entirely on time.
Right.
And from there, you move to a fishbone diagram to really dissect the root cause. It literally looks like a fish skeleton.
Yeah, it's a great visual.
The head of the fish is the primary failure. So late pizza deliveries on weekends. And then the bones branching off are the potential categories of failure: machinery, people, methods, and materials.
It forces this completely holistic view of the ecosystem. Like under machinery, are the delivered cars constantly breaking down? Under people, are we experiencing crazy high driver turnover? Under methods, is our whole dispatching algorithm completely broken?
Or under materials, are we constantly running to the back room for more dough?
Exactly. It stops managers from just lazily blaming the delivery driver for being slow.
It separates the systemic disease from the visible symptoms. But let's say you isolate the disease. You realize your dispatching method is flawed, right?
Mhm.
So you implement a shiny new software system. You are now in the improve phase.
Sure.
How do you actually prove to your stakeholders that the new process is mathematically capable of meeting customer demands?
And this brings us to the most complex math in our sources today, proving capability. I'm actually calling this part the Great Cereal Box Crisis.
That is a very grounded way to look at the process capability index, honestly. Also known as the CPK. CPK is the ultimate mathematical acid test. It measures how neatly your actual production data fits inside the design limits you promised to the consumer.
Let's paint the scenario for you listening. Imagine you run a factory producing a really popular cereal. The box boldly advertises exactly 16 ounces.
Naturally.
But Consumer Reports just published a scathing hit piece accusing your company of ripping people off with underfilled boxes. Now, the government regulations state you are allowed to be within plus or minus 5% of that advertised weight.
Which establishes our hard boundaries. So 5% of 16 ounces is 0.8 ounces.
Right.
Meaning your upper tolerance limit is 16.8 ounces
Yeah.
and your lower tolerance limit is 15.2 ounces.
Right.
Any single box that falls outside that specific window is legally considered a defect.
So we panic, we pause the line, we pull a sample of 1,000 boxes and we weigh them, and the data comes back. The average weight, the mean, is 15.875 ounces.
Okay, so a little under 16.
Yeah. Then we look at the standard deviation, which measures the spread of our weights, and it's 0.529 ounces. We plug this all into the formula, and it gives us a process capability, a CPK of 0.4253.
And in the world of industrial statistics, a CPK of 0.4253 is basically a 5-alarm fire.
Well, here's where it gets really interesting, and honestly, where I get tripped up looking at these slides. Our average weight is 15.875 ounces, right?
Right.
The legal minimum is 15.2. We are technically inside the legal window on average. So why on earth does this formula output a failing CPX score? That feels totally contradictory.
I'm so glad you brought that up because it highlights the single biggest trap in quality control, trusting the average.
Really?
Yes. CP does not just look at your mean. The formula calculates the distance from your mean to the nearest tolerance limit and then divides that by 3 standard deviations. Your standard deviation is 0.529.
Which is bad.
That is massive because your data is wildly scattered. Yes, the peak of your bell curve sits safely at 15.8, but the base of your curve is so wide and sloppy that the tail end is bleeding heavily over that 15.2 ounce cliff. You are literally boxing up air.
Oh, wow. So Consumer Reports was entirely justified. The average was just a lie hiding a massive spread of defects.
Precisely. A QB of less than 1.0 mathematically guarantees you are actively producing defects because your normal variation is wider than your allowed limits. Most standard manufacturing aims for a minimum QB of 1.33.
And what does that get you?
At 1.33, your bell curve is tight enough that you are only making about 63 mistakes per million opportunities.
Which sounds incredibly tight for Certa factory, honestly. But if we go back to the Six Sigma standard we mentioned earlier, 63 mistakes per million is totally unacceptable. Six Sigma demands a TPK of 2.0.
Exactly. At a Krepintek of 2.0, your bell curve is so thin, so rigidly controlled, that the chance of a box falling outside the limits drops from 63 per million all the way down to 2 per billion. You have mathematically eliminated the possibility of a defect under normal conditions.
Okay, but let's say we overhaul the factory. We achieve that beautiful Krippentek of 2.0, we throw a party, but the laws of physics still exist.
Sadly, yes.
Conveyor belts stretch out, gears wear down, tooling gets dull over time. How do we spot a machine degrading over time before it starts bleeding defects and ruins that perfect treat cast?
That transitions us perfectly into the final control phase of DMASE, which relies almost entirely on control charts. Think of a control chart like a continuous EKG monitor for your assembly line.
Oh, that makes sense.
Yeah, you plot samples over time against a central average line, and that's bracketed by an upper control limit and a lower control limit.
And the notes specify these limits are usually set at plus or minus 3 standard deviations from the mean, right? Because statistically, in a normal distribution, 99.7% of all common cause variation will naturally fall within those 3 standard deviations.
That 99.7% figure is so critical. It means if a data point suddenly spikes outside those lines, there is only a tiny 0.3% chance it was random luck. It is basically a mathematical siren screaming that a special cause has infiltrated the system.
But I see several different charts listed here in the sources. There are P charts, C charts, X-bar charts. From a high level, just plotting dots on a graph seems pretty universal. Why split hairs over the specific type of chart?
Because the underlying math changes entirely depending on the nature of your data. You cannot plot discrete pass-fail data the same way you plot continuous physical measurements. Like if you are tracking the proportion of defective light bulbs in varying batch sizes, you use a P chart, which is based on the binomial distribution.
Right.
But if you are counting multiple flaws on a single continuous unit, like the number of scratches on a single pane of glass, you use a C chart based on the Poisson distribution. And if you are tracking physical variables like weight or length, then you use mean and R charts.
Got it. And the visual patterns on these charts are fascinating to me. You aren't just waiting for a dot to cross the red line. You are looking for behaviors.
Yes.
For example, the notes say, if you see 5 consecutive points trending steadily upward, even if they are well within the safe zone, that is a glaring red flag. Or if the points start zigzagging erratically, jumping from top to bottom, it's like the data is whispering to you, hey, a tool is wearing out or raw material just changed. You can investigate before a single defect is ever produced.
But here's the brutal friction of reality. Generating those charts requires inspection, and inspection requires human labor, expensive sensors, and time. And this introduces a mathematical dilemma regarding the cost of quality that companies constantly get wrong.
Oh, this is the eliminate QC or not problem from the deck. I love this scenario because it just obliterates traditional short-sighted corporate cost cutting.
It really does.
Here is the setup for you listening. A company wants to trim their budget, so management proposes firing a quality control inspector. Now, this inspector costs $9 an hour in wages, and they check 50 units an hour. Historically, 4% of the incoming parts are defective. If the inspector is fired, those defects will bypass the checkpoint and escape into the final assembly, where fixing them will later cost $10 a piece.
And on a spreadsheet, cutting that $9 an hour job looks like an instant win for the payroll department.
But let's run the actual live math. The inspector reviews 50 units an hour. With a 4% defect rate, that means the inspector catches exactly 2 defective parts every single hour.
Okay.
If management fires the inspector, those 2 defects slide down the line. We know fixing them later costs $10 each. So 2 defects times $10, these escaping defects are now costing the company $20 every single hour. The inspector only costs $9 an hour. By firing the inspector to quote unquote save money, the company is actively losing $11 an hour. The math is undeniably bad. So why does management still try to make these cuts in the real world?
Because the cost of quality is notoriously fragmented across different ledgers. The $9 an hour inspector is a highly visible, easily targeted expense right on the floor manager's direct budget.
Yeah.
But the $10 replacement cost, that gets buried 6 months later in a customer service budget, or warranty claims, or just a slow bleed of brand loyalty. It takes really holistic business thinking to realize the $9 is actually an investment protecting the company for the $20 penalty.
Man. So we have control charts, Six Sigma limits, DMAIC methodologies, but all of this relies on either sampling after the fact or mathematically managing the magnitude of errors. If inspection is so fraught with hidden costs and human oversight, can we just prevent the defect from happening entirely?
This is where the source material introduces a radical paradigm shift. It's called the Shingo system, also known as fail-safe design, or
Right.
Shingo argues that SBC and Six Sigma are fundamentally flawed because they assume defects are inevitable and just try to control the blast radius. Shingo assumes defects can be completely prevented through 100% inspection before the fact.
But to grasp this, you have to understand a vital distinction the sources make between an error and a defect.
Yes.
Errors are caused by human beings. We get fatigued, we get distracted, we grab the wrong tool. Errors are just inevitable. A defect only occurs if that human error is allowed to physically reach the product. Shingo says we must catch the error via immediate feedback before it mutates into a defect.
And crucially, 100% inspection in the Shingo model does not mean hiring an army of $9 an hour human inspectors. It means engineering the inspection directly into the physical process or the tool itself.
So what does this all mean? Let's bring it down to a familiar daily frustration for you listening. Think about writing an important email. The Six Sigma approach is like carefully proofreading your draft, tracking your historical typo rate, and hoping you catch your mistakes before you hit send. You are inspecting your own work.
Just stressful.
Right. The Shingo Kobyok approach is when you type the phrase, I have attached the file, you forget to actually attach the PDF. And when you click send, the software instantly blocks you with a pop-up saying, wait, you typed attached, but there is no file.
That is a perfect example. And this raises an important question about how we view human nature within industrial systems. The absolute brilliance of the Shingo system is that it completely removes the burden of perfection from the worker.
It's so forgiving.
Exactly. It accepts the reality that human beings are neurologically incapable of flawless repetition.
Yeah.
Therefore, the system itself, the machine housing, the software architecture, the physical assembly line must be designed to physically reject the error.
Right.
Like a plug that is shaped so it literally cannot be inserted backwards. Or a machine press that will not activate unless the operator has both hands safely pressing two separate buttons.
It's human-centric prevention instead of statistical reaction. So we've navigated a pretty intense mathematical landscape today. We started by identifying variation, the red lights and the wandering cows, as the ultimate adversary of precision. We unpacked the heavy statistical artillery used to combat it.
The Six Sigma pursuit of 2 defects per billion.
Right, and the DMAOC playbook for turning customer complaints into structured data. And of course, the quality calculations that expose when a company is really just selling you a box spare.
We also explored why the underlying distribution of your data dictates the specific control chart you use to monitor your process, and why short-sighted cost-cutting on inspection always costs you more in the end.
Yeah.
And finally, we looked at the elegance of the Shingo system, which stops the defect from ever materializing by fail-safing the environment. Ultimately, whether you are managing a global supply chain, running a small business, or just trying to organize your personal finances, learning to spot your own process variation and building fail-safes into your routines can save you massive amounts of time and friction.
The pursuit of quality is never an accident. It is a meticulously designed defense against chaos. But looking at all these tools, I'll leave you with a final thought to ponder that actually isn't found anywhere in these slides.
What's that?
Well, both the dense Six Sigma statistics and the physical fail-safes of the Shingo system were explicitly designed for a world where human beings are the primary operators and the primary source of variation. But as artificial intelligence and fully autonomous robotics rapidly take over these services, effectively eliminating human error entirely, what happens next?
That's a great point.
Will these traditional control charts become obsolete relics of the 20th century? Or will AI, operating at speeds and logics we barely comprehend, introduce entirely new, bizarre special causes of variation that we haven't even named yet? One way or another, we'll still be trying to decode the hidden machinery, hoping that MRI machine takes a clean picture.
What do you think? Better than my 1.5 hour lecture? True.
No, useful, but
What's missing?
detail, depth, the fact that given circumstances for what they're describing is, yes, useful, but
What do you mean yet useful?
what I mean is it is useful to an extent, but this one-on-one and your disposition when it comes to like how you teach and what information.
There's no
you're getting,
nuance.
Yeah. So
Well, I was gonna dismiss the class now, but then you mentioned that. No, this was just an introduction. I will fill in whatever little I know so that to explain a little bit more, especially when we talks about the use of statistical process control to determine when you are monitoring and controlling a process. That particular process you want to, the variation that you want to see are those that are part of the system, inherent in the system, like in the traffic example that these couple of podcasters use, is that the traffic lights, as part of your commute, the length of commute is affected by the presence of traffic lights, and that's part of the system, so something that you cannot control. But there are times that, especially let's say that you live in Medford and you've commuted many times enough between Medford and school, that it will take you 20 minutes on average. And there will be some variation there, maybe a minute or two, give or take. But sometimes there might be an accident on I-5. That's a special cause variation because that would cause your travel time to be significantly more than the average. Okay. So in quality assurance, when you're looking at control charts, you're actually using that as a visual indicator for presence of special cause variations. Yeah, a good typical example I use in class when I talk about control charts is that an example would be maybe your body temperature. Right, your body temperature, there is an upper acceptable limit, and then there's a lower acceptable limit. But we are to expect a body temperature of 98.6, right? 98.6, 98.6. So if you were monitoring your body temperature throughout the day on an hourly basis, you will see some maybe random occurrence of this body temperature if you are healthy. But there are times when your body temperature rises above the acceptable limit. So in this sense, when you measure, say, 101 or 100, you're talking about a body temperature that is outside the acceptable range, and that indicates a possible something is going on in your system or in your health, right? It is an indicator that needs to be checked. It could be some infection or fever or cold or whatever that needs to be.
Could also
Yes.
relate to environmental chemistry. So you could consume something that could lower your core temp. So
Okay.
for instance, drinking coffee might make you feel warm, but it actually lowers your core temperature.
Okay. But the point here is that when you observe something like this, there is a need for you to investigate and find out the cause, whether it's really something that is maybe a symptom of a physical issue. Yes.
So thinking about like practical application
Okay.
for like industrial manufacturing, do they have like an actual computer program that's like tracking,
Yeah.
using all of it and you get like real-time updates?
Yeah.
Is that something that's custom coded or is that something that you purchase off the shelf?
Well, it depends. There are statistical packages out there that you can use to just plug in the data, the sample, the observations, and then they'll track that for you. So,
Any like common names of software?
well, Minitab, SPSS, My Template.
Okay.
Yeah, I've got that. So I'll show you. We'll look at some problems.
Okay. So
Okay.
Thank you.
Rose, you were raising your hand, or somebody
No,
else? Was-
I was just stretching or moving my yarn around.
Oh, okay. All right. Okay. So what was that? Talking about the control charts as a way to monitor if a pattern is present in a chart that indicates a potential likely a presence of a special cause variation that needs to be investigated. And if it's a problem, corrective action needs to be taken, right? So an example that they gave was this pizza delivery, and the tool that they're using to monitor this kind of defect is the number was late deliveries. All right, using the 80-20 rule, that this is a big problem that they are observing, and they try to figure out the cause that caused this unusual number of late deliveries. And the tool that they're using to determine or investigate the cause is the Pareto chart, otherwise known as the fishbone diagram. So these are these four branches of this fishbone diagram are the machinery, the people, the methods, and materials. So identifying which of these caused the late pizza delivery, that corrective action can be made. Okay, so what else did they talk about there?
Renee,
Yes,
sorry, before you move on,
sure.
can you explain, is there any methodology behind the directions of the arrows?
The what? The direction of it? Not necessarily. It's just leading up to, these are causes, and that's the effect.
But as far as the, I understand the red, but the smaller black arrows on each red.
Oh, I think they are sub causes. So, for example, if you have unreliable cars, deliveries, that's one. And then maybe the low pay, no money for repairs, kids own junkers.
The directions of those arrows.
Yeah, pointing to a major potential causes.
But there's some that are going like down towards the spine and away from the spine.
Right. Like, for example, this oven's too small.
You're like high turnover, poor training.
Right. Yeah, that doesn't make sense, does it? Like a high turnover, that probably should be more on the people. The poor training and then the poor use of space would be a cause for oven too small.
Renee, would the fishbone ever be used in like project management, like flow, or is it strictly for
Possible, yeah.
problem identification?
I think you can use that too as a tool to identify like bottlenecks. So it's just a way to analyze problem areas or causes of problems in the process. Okay. So I think in this particular slide, we started this term about talking about, I mentioned that in any kind of process or anything that you do, try to make the process as consistent as possible, meaning minimize the variation in the process. Because by eliminating, or you cannot really eliminate process, because it says that every process exhibits some form of variation. You can only reduce variation. Okay? How do you do that? So that's a common cause variation. It's part of the process. You can minimize the process variation through improvement of the process. A good example is the process of duplicating materials. It can range from the most manual. You copy, you write, right? So if every page maybe that you write, there will be variation among the words or how you write the letters. But there will be consistency, right? And as you write more and more pages, the writing will deteriorate, right? Why? Well, at that point, you're already introducing a special cause variation, which is probably because you're getting bored, you're getting tired, right? So how do you eliminate that special cause variation? You take a break, right? So manual writing, was in the old way, in the old days, monks would write manuscripts, right? And then now, well, in the maybe what 50s, 60s, they used what typewriters,
So
and then the typewriters. How did they? For those of you who are probably old enough to remember that, they reproduce documents through, what do you call that machine?
Photocopiers,
No, photocopies came later.
Predecessor.
printing press,
no.
like that, because they also.
Videographic machines.
There were typewriters, you could print using little metal letters and put it onto the printing press and print things.
Right, yeah, but yeah. So if we were printing exam materials, for example, here, we would, in the past, I used to do this. We used mimeographic machines.
Yeah.
You guys are familiar with that technology? Right?
Yeah.
Look it up.
We had to cover a bit of that in typography.
It's there, it's floating.
But the point I'm making here is that every improvement in technology, there's a change in the quality of the print. So the process changed here. Now we're using laser printers. And if you're looking at a document printed by a laser, you cannot see the variation. There's variation in the letters, but to the naked eye, they are not visible. Okay, at that point, we have already reduced the common cause to a really small amount. So, process improvement is the only way that you can reduce variation in the process.
Did you take back with the typewritten?
So, let's focus now on this identification of a special cost variation that is if you are monitoring a particular process. And here's the important slide that will tell you what kind of control chart to use. Okay? So, what are the components of a control chart? A control chart will have these three components. One is the middle value, the average, if you will, or the nominal value. Like in this body temperature example, that's the 98.6. Okay. Then you have what we call as the upper control limit. Anything that is within the upper control limit and the lower control limit is an acceptable measurement. Okay. Anything outside, obviously, is an indication that a process is not in control. So, in determining the appropriate control chart, we have to understand the difference between the podcast talked about this. The difference between an attribute and a variable. So it depends on what data you are trying to observe or measure. So if you're counting, the key there, counting. If you are counting the number of defectives or number of defects, then you're talking about data that is an attribute. Okay? Whereas if you are trying to observe something that is measured, length, weight, grade, right? Then we're talking about a variable. So in a variable, we will usually measure that in terms of averages. Average weight, average length, average width, right? Because it's something that is measured. So there are two charts that we will use when you are monitoring and controlling a data that is measured. And those two charts are known as the mean chart, oops, mean chart, view. Do that for me?
Oh,
Now it's
something came up, but I think it's partly because you have that selective.
No.
you probably have to deselect that box.
There you go. Let's forget that. The average, the average which measures this part here, and the standard deviation, which measures the width of this control limits. Okay? If you are dealing with an attribute, there's only one kind of chart that you will construct and use to monitor. Either you are using what is known as a P chart. Okay, so what is a P chart? A P chart is used when you're observing the number of defective units in a sample. In other words, a P chart is when you can express the number of defectives in a group. Okay, so if I'm inspecting, say, 100 widgets, each one I'll test. And if I observe one that fails out of the 100, I can express that as 1 over 100, or a proportion of 0.01. Okay? So again, if you're observing the number of defectives in a group, then the appropriate chart is the P chart. The C chart, on the other hand, is used when you're observing the number of defects or imperfections or whatever it is you want to observe in an observation, or in a single unit. So if you're working, say, in the production or a company that produces veneer products, maybe for every sheet, 8 by 10 sheet of veneer, you will count imperfections. Okay, so in a particular sheet of veneer, you can have X, the number of defects will range from 0, 1, 2, all the way to infinity, meaning there is no upper limit. That is in a C chart. Okay? Whereas in a P chart, here, X will range from 0, 1, 2, all the way to the sample size N. There's a finite number of defectives that you can observe when using P chart. Are we clear? Okay, so let's apply that now to these problems. Now, Brian wants to understand the formulas. Brian, these are the formulas that were used in constructing the mods or the charts. But
That's practical.
for us, it's really, we don't want to mess with that. Okay, so I talked about the control limits, the 3 parts. So the red solid line here, upper limit, lower limit, and the dashed line is the nominal or the average. The blue dots represent your sample statistics, whatever it is you're observing, whether you're observing an average or a range, which is a measure of variability, or it can be the proportion, it can be the C chart. I'll get back to this, interpret this again. So let's look at this particular problem. We can always refer back to that slide where we defined attribute and variable, okay? So the process involves computer upgrades, and they have a nominal time of 80 minutes, meaning maybe historically or in the past, this particular process, computer upgrade, will take an average of 80 minutes. Okay? And there will be some variation from the 80 minutes. Samples of 5 observations each have been taken, and the results are shown below or in this table. Okay? Now, note that there is a difference between the term sample and number of samples. Okay? So, it says here, samples of 5 observation. So, how many samples are there?
5, 6.
No.
6 times 5,
How many samples are there?
30.
No, those are observations. A sample is a group of observations.
6.
So you're saying one.
A group. So here's 1. No. 6 samples.
I already said that a long time.
Oh, I heard 6 times 5.
Well, that's me because you said there
Yeah.
were 6. I went down rapid.
Sorry, but yeah, there are 6 samples. Each sample has 5 observations. Okay? I need to make that clear because if you said you have 6 observations, 5 samples, you will enter this row of numbers, which is the incorrect set of data. Okay? Now, next question. Are we dealing with an attribute or a variable? What is this distinction again between attribute and variable?
Variable.
No. Attribute is something we,
Count.
variable is something we measure. Okay. So each of these observations, what is it each one? Is it a count? Or is it a measure? Like the 79.2. What is it? Is it a count?
Is it a measurement of time?
It's a measurement of time, correct.
So it's a variable.
It's a variable. Yeah. Okay. You guys agree?
You
I'm
don't
sure
count
you
minutes
guys-
and measure time.
Huh?
You don't count minutes, you measure
Yeah, you're measuring time.
time units.
A measurement is something that is continuous. Although we say 1 minute, 2 minutes, 3 minutes, but really, we're just rounding it to a unit that is easily observable for us. But really, time is a continuum, right? 2 minutes and point something seconds. So are we clear there? Okay, so this is a variable. Now, let's go to the quality control charts. Go back to the main menu. You'll find the control charts here. And if you are computing at the Six Sigma using the DPMO model, use that. And if we're dealing with a variable, what were the 2 charts that apply?
Bar and armor.
X bar or mean and range. So for variables, some things that we measure, we will use the X bar chart and the R chart or the range chart. And the X bar chart monitors the average of a process, whereas the R chart monitors the variability of a process. For us to say that a process is in control or performing as expected, both the R chart and the X bar chart must be showing random. When you plot your data or your observations in the chart, they must be random. Anytime that you observe some form of pattern, indicates the presence of special cause variation. Okay? And when we talk about patterns in quality control, it's associated with probabilities. Now, so for the mean chart, in constructing the mean chart, you can use this one. It says mean and range chart for variable when the process standard deviation is given, is known. If the process standard, this is unknown. Excuse me, sigma unknown. If the process standard deviation is known or is given in the problem, then use this model. Okay?
And then when it's unknown, we're supposed to take an average and then.
For the unknown, there's a chart will compute. It uses a particular table, so you don't have to. If you were to compute those by hand, you will be using this table. But you will not, because this is embedded into the model. All right? Okay, so let's go back to the problem. We know that we're dealing with a variable. So we will be using the mean and range charts, but which one? Do we know the process standard deviation? I say process standard deviation, I'm talking about the population standard deviation. It's not, okay? So it's not given there. One might say, oh, I have these observations, 30 observations. Can I compute a standard deviation out of those 30? The answer is yes, you can. What kind of standard deviation is that? Well, that's what we call as the sample standard deviation, which is different from sigma, the population standard deviation. Okay, so let's copy that. I think, wonder if it's already in the proper format. All right, we will use the second model. All right. Okay, see how the template is structured? The samples are in rows, whereas the way that the problem is presented here, the samples are in columns. So we need to transpose. Okay, we don't want to retype these numbers. We can use, let me open a new worksheet here, and I'll just copy the whole thing, including the sample number. Okay, so transpose, convert columns into rows, rows into columns. Copy that. And then we can paste it anywhere in the worksheet. So we'll do one of the options in the paste options is transpose over here. You see that?
Yeah.
Now your samples are.
So it goes across instead of down.
Because the orientation of the template is, I can copy this. The orientation of the template, the observations are row by row. Okay?
No, can you do that one more time?
No,
Which one? Transpose.
Transpose, So I'll copy this.
Mhm.
And then I'll paste transpose here. Paste special. And one of the options there is transpose. Okay. I'll copy that. And I'll just paste that here. Delete that. There's your chart created for you. Two charts. The X-bar chart, which monitors the average of the process, and your range chart, which monitors the variation of the process. So, how do we read charts like this?
If it's outside of the upper limit and the lower limit on the X bar, then you have a problem, right?
What we should say it again, please? If
it's above or below.
what is it?
If you have a measurement recorded above or below the
limits.
limits, then you have a problem.
Correct. Well, that's an indication of a
Defect.
potential, not defect, but that the process at that point has gone out of control.
Out of the
That
range of
needs to-
acceptable limits.
Correct. That means that you need to investigate what happened at that point. Was it the operator? Is it the machine, the material? These are sources of these are special cause variations. So here's how we will read charts. Okay, so normal behavior says everything that you observe there is random. Okay? Common cause variation should only observe. Anytime you observe a pattern, such as this, increasing 5 successive points, increasing 5 successive points, decreasing, or any time that you observe, as Lawson said, anything that you observe above or below, that's a possible indication or a very likely indicator of a process that is no longer in control at that point in time. Okay, now the question is, why would that be considered as an indicator of not in control process? I said earlier that patterns are associated with probabilities. Okay? If we're talking about a 3 sigma or 3 standard deviation process, we are to expect 99.7% of the observations to fall within that range. The probability that an observation will fall outside that range, either this or this, is 0.3%. Okay, so we say, hey, we're observing this. Now, if we assume that the process was in control at that point, and yet you're observing it. So when you're observing it, you say that it's not a random occurrence. Does that make sense? Okay. Oh, I wish I brought I gave a test to my undergrad operations management this weekend, and I compare scores term to term. The same exam, it's the same material, the same degree of difficulty, E or ease of the same measurement instrument. If I'm going to compare the average of, say, exam that I gave this term versus exam I gave last term, what should the average be? Different or the same?
Different.
It might be different, but close, correct. But guess what? When I plotted the exam scores, well, this is still related to the class material, right? So here's what happened. Oh, wait a minute. I think I have a better. Let me clear that first. There's some sensitive material in my. I might be showing sensitive material in my email.
We held up on that one though.
That's right, it's just too small. This is really very interesting. And it still relates to this class. Okay. So I shared this with a faculty, Mike. So this was about exam 1 from 2 asynchronous online cohorts. So it's some kind of what they call characteristics of classes. Spring 2022. Free AI availability, and spring 2026. Okay. The comparison is based on 2 groups that were held constant across relevant dimensions. So if you're doing a before and after or A/B testing, did you guys talk about it in marketing? A/B testing?
Blind. I know what it is, but I don't know if we talked about it much.
If you're trying to test the different marketing materials, you can compare effectiveness by doing an A/B testing So it's similar to, so when you do A/B testing, you have to make sure that all other variables are controlled. And in this case, same exam questions, same course content, same online delivery format, same student profile. It's important. Both exams administered online. Both exams open book, open notes with access to online resources. Okay?
So,
There are the results. This was this term. And it's from 0 to 100. And this was in 2022. What do you think?
Is it harder?
I don't think we're getting anything past you.
I know but what I mean, if I were doing this as if I were doing a report on the use of AI as part of an assessment,
so it improved.
you obviously here this one a much significantly higher average. Now, in my 30 years of teaching operations management, it's very seldom that a student gets 100. And look how many students got 100 in that.
Oh, that's the AI.
That's the AI. Yes.
That's okay.
So just out of curiosity,
Uh-huh.
you're assuming that the only variable that changed was the presence of AI.
Yes.
Did you calculate like average GPA?
It just say profile of students.
Okay.
Yes.
What if I'm a genius?
Don't be a genius this term. But I asked AI ChatGPT to analyze this, and this is where I think reliance on AI is good for certain things. I asked AI to plot the distribution. That red thing is AI generated. Same thing here. But AI said this, which it's not true.
Students are learning the concept better utilizing AI.
Yes, suggestions are mastering the material more consistently.
I think
Believable or not?
Capable. That way they're not dependent on the teacher.
Same teacher,
I think we're all here to learn, but we have the ability to like check our answers. We're
Yeah.
gonna check our answers.
You can check your answer.
That's fine, yeah. I mean, I definitely learn it. But I want to make sure I have a financial obligation to have a good grade.
Yeah. Maybe we should do.
So, guess what I did? So this is now the special cost variation. I observed it. There's a corrective action. The second exam, so exam one, I reduced this was all set at the beginning of the term because I observed this pattern last term. Reduce the weight from 25 to 15. So less. In this exam two, it's proctored. So off limits, AI is off limits.
Is it still open book?
It's all open books. But so was last terms. I mean, in 2022.
So is that saying that people did worse on the proctored exam?
Yeah, they will. In fact, they did when I taught for winter 2026. When I compared exam one to exam two, big drop. I've seen students get 100 on exam one, 45 on exam two. Now, what's the difference in the variation? The availability of AI as a tool to obtain the answer.
What do you care?
What?
What do you care?
Of course I care.
But why?
Why?
What do you? I honestly, what do you care in the sense that like?
He wants us to learn, not cheat.
No, I understand that, but I'm curious if you have more failure rates, people are less likely to take your class or what were we talking about? Credit hours, CHs, and so Renee's classes are too hard, and we're not going to take him, and then you get boycotted, and then you lose your job. I mean, I don't understand.
Hey, hold on, tender, man. No, seriously. We have learning objectives, right? When we teach classes. So, what do I care? I want to make sure that my students, when they go out there, that they have the basic knowledge on that.
But it doesn't matter how they get in the
Of
answer.
course it does.
Why?
Because if they get the answer by just copying the question and plugging it into AI, and the AI spits out the answer, do they learn? Is that a measurement of learning?
Does it matter if it's correct?
Of course it does.
But why?
It was some measure of.
So there's a philosophical difference here that we and I can come back to, but
Yeah,
it's curious, and I do think that it has to be factored into the future of education.
well, the question is, they really understand.
So
It's the, and understanding is that we're trying to, from an assessment standpoint, it matters. But from a, if it's your job, then it doesn't matter. It's your,
long division written out versus using a calculator, same answer. What does it matter?
It's just a theory.
well, the application is that you understood the problem, you understood the question. The tool that you use is what makes it.
I will agree with you there.
You just have to know how to do long.
Thank you. You get an A today.
So,
Easy A.
Yeah.
so, like to Lawson's point, it's not going anywhere. It's
No.
it's a reality.
Right.
You're noticing that it's making a difference in, let's call it the quality of education.
I don't know.
Or maybe the quality
Well,
of
eventually.
the applied education.
Right,
Sure.
right.
So what would you do to that? Like, what would be something you would do to address that?
Guess what? Because here's my concern, okay? Here's my concern. The concepts in the first lead from one to the next concept. If they did not understand those concepts in exam one,
Mhm.
they're not going to do well in exam two, which is proctored.
I see. Okay.
So why do I care? Because I want my students to perform just as good, just as well when there are no guardrails or whatever.
So does that mean that moving forward, it's more likely that there will be more proctored exams?
It depends. I mean, that's, I think, that is a discussion, you know.
I gotta say it all over. It's like, yeah, there's gonna be more.
Yeah. So put it in your case. When you take your major field test, it's proctored and no resources available to you. So if you skated by using AI, copy paste, getting the answer, getting 100%, and when you get to that point where you're tested, I mean, it doesn't have to be just a major field test. Maybe it would be when you are applying for a job and there is an exam.
Or
Should do paper exams.
What?
Paper exams.
Yeah, but face to face you can do that, but online,
Yeah.
that's it.
I nailed it.
I don't disagree with that, Jim.
Yeah, hey, no, I think we're getting off subject, but you see the point here, right? When you're related to this concept of controlled charge, you want to observe changes in your changes in what you're measuring, so that you can you can provide explanation.
Put that on my headstone.
No,
Disturbing, but not surprising.
it was, oh, that wasn't supposed, you were supposed to see that.
So as far as the lower control limit and the upper control limit, there's always 3 sigmas.
Not necessarily, depends on the confidence level that you want in your conclusion. Sometimes 95%. This all goes back to statistical analysis, the type 1, type 2 error. I really don't want to, but you can read up on it. What are the types of errors in hypothesis testing? There are 2 kinds. Type 1 is when you reject a true null hypothesis. I know it's a technical jargon. And the other one is failing to reject a false null hypothesis. In the area of medicine, so one is a false positive, and the other is a false negative.
Type 2 is a missed.
Yeah, so, you know, if you're talking about in medicine, which one is worse, false positive or false negative?
False negative.
They're both. It depends really on the situation. If the false positive means amputation of an extremity, that's bad, right? So it relates to that. The 5% or 1% or whatever an area, depends on the cost associated with making that kind of error in hypothesis testing. Okay.
Renee, on the
Yes.
limits on the upper and lower end, they're statistically driven out of how much sampling? Like, where do those come from?
The number of samples?
Just your upper and lower bands, like,
Oh, that's based on what you observed in the past. In this case, the upper, well, maybe I should show you the formula so you can have a better appreciation for the upper control. So the upper limit is based on the average plus,
the deviation.
well, yeah, associated with a certain confidence limit, 3 sigma or 2 sigma, and then the variation. So that what in stats we call that the margin of error. Okay, so that would be that. And then the difference between this seriously. So the upper and control limit are dictated by 2 things. Well, actually 3 things. The confidence level, which is Z, sigma, the variability of the process, and then sample size. Yes.
And what is the D4 and the D3?
Oh, yeah, well, that's when the population standard deviation is not given. The D4 and D3 are approximation of that replacement of this here. When we're talking about the range, yeah. 2 D4, D3 over here. D4 and D3 is that, like I know, that's the confidence level. An approximation. Okay, so are we clear here in terms of what can constitute an indicator of a process not in control? Maybe here's a question. Why would this be considered as a process not in control? Well, this is erratic behavior, meaning you have many observations close to the limits. Why would that constitute an out of control process? Well, because if you look at
They're not following the average, correct? They're not near the average. Then
because they're not near the average. Because if you're looking at the distribution of the sample, it's like a normal curve. The probability of observing this is a normal curve, like rotated 90 degrees to the right. That the probability of observing a point close to that is very small. So when you're observing many of those, say, hey, that's not supposed to happen, and yet it is happening. So are we good with this? Computer upgrades? How about, why don't you do this on your own using your, go through the questions again. Are we dealing with attributes or variables? If you're dealing with variable, then use the mean and range chart. If you're dealing with an attribute, then either the P chart or the C chart applies. In this problem, we have a medical facility that does MRIs for sports injuries. Occasionally, a test yields inconclusive results and must be repeated. Using the following sample data, we're in sample size is 200. Determine the upper and lower control limits for the retests using 2 sigma limits, meaning 2 standard deviations. So for a control chart, this would be 2 sigma. This would be 2 sigma. Recall your basic stats using the standard normal distribution. 3 sigma, we expect 99.7% to fall within that range, right? 2 sigma, how many percent? What percent? Slow. It is lower than 99.7.
95.
95
0.45.
95.
0.45.
How'd you get that?
That's AI.
No, I did not give you the right answer.
Standard deviation.
Above and below.
Okay.
We ran into an issue where we were trying to check our answers, but it was trying to change a formula by removing a -1 at the end of the formula.
What do you mean, -1?
It was one of the last.
That's a study,
sections.
you're probably talking about S is equal to X minus X bar and minus 1.
Yeah, no, it wasn't that formula.
Yeah.
It was in
No, there's nothing there.
test.
Oh, the forecasting, no, we're not.
Meaning that sometimes the AI wants to alter a formula to.
Yeah, that's why we have to be very careful when we still need to know
Why you can't
what we're doing when we have, when we use AI. So what do you think?
Say it was.
I don't know, I haven't said anything. You guys have.
What does AI say it was?
Oh, he was just talking about what is 2 sigma, and I said 95.45%.
Oh, okay.
So what are we dealing with here? Plug it into AI and see if it gives you the right answer.
Yeah, ChatGPT.
Are we dealing with attribute or variable?
Down here. Why are you looking at me? I don't know. I'm learning with you.
Secret boss.
I don't have anything set up. I really am for specific use.
This is
So.
I'm sorry?
very
What did you say variable? Are you measuring?
inclusive results, right?
No, you're not. What do these numbers represent? This. So focus on that, the observation.
Oh, okay. So that
It's an attribute.
Why?
because it's the tests.
Now, it's a test.
It's observations, right?
Yeah, it's always a variable, is also an observation. But what kind of observation are we dealing with? Is it something we count or is it something that we measure?
It's
You count
measured
this.
by-
We count. Okay, so there's the answer why it's an attribute. We're counting the number of retests.
But an MRI gives you a measurement.
Oh, no, just say this is just talking about each MRI either yields a conclusive result or inconclusive result. Right, it's one or the other. So these are counts.
Yeah, attributes.
Right, attributes. Are we dealing with a P chart or C chart? What was that? P chart, Katie? Yeah. Why? You're observing one retest out of 200. Okay? So we can convert one as a proportion. So we know that we're dealing with a P chart. I'm just gonna copy this again. And
So is the answer to that particular question, so is the processing control, like, is the answer either yes or no? Is that the type of answer? That question?
yeah, you can, or either it's really not a definitive yes or no, but we'll say very likely yes, very likely no.
I see.
We're dealing with probability.
The process becomes out of control at sample 10.
Okay, so let's complete this for class. Okay, so the data is represented in column.
Yeah.
I need to transform again. Transpose. Okay, copy. And then no. Copy that. Paste here. Okay. Okay, there's one thing I need to change here. What is that?
Sample size is incorrect.
Number of sample or sample size should be
200.
Yep. It is correct from the data.
I think that number 8 has to get turned into a.
3, thank you. Yeah, that looked kind of weird.
I think that's the only change you have to do.
Okay. So here's the proportions chart. And if you were reading this, if you were the quality control for Asante and you were monitoring the MRI readings, is there a cause for concern? On
That.
the 10th observation, you observe more inconclusive results more than your typical. So from a quality standpoint, you will go back to that period and investigate the source of that unusually high proportion of inconclusive results.
So in this case, would that just be like a recalibration of the machine, or is the operator, or is it power?
Correct. That's why you have to investigate.
Yeah.
So it could be there are many reasons. It could be that the machine may have been defective, at least not performing at that time, or maybe you had a new technician, right? So you have to investigate the source of that. Okay, and then it says eliminate. Once you figure that out, eliminate that. You can just delete. That's this point here. You can just delete that. Everything will go back to. Okay. Next question about this? Yes.
How did you change the confidence levels to 96?
This one you can just do scroll versus. You can use the up arrow, or you can just type it.
It might not work on the Mac.
Maybe your macro is disabled because that is a macro control controller.
Thank you.
You're welcome. All right, next. The postmaster of a small western city receives a certain number of complaints each day about mail delivery. Assume that the distribution of the daily complaints is Poisson. Poisson is one of the distributions in stats that is used to find probabilities of occurrence within a given interval. Okay. You see this distribution again when we talk about waiting lines theory. We are to construct a control chart with 3 sigma, so 3 standard deviations using the following data. And then we are to answer if the process is in control. So same question as before. Are we dealing with attribute or variable? Again, focus on what these numbers represent.
These are attributes, right? These are the number of complaints.
Correct.
So,
It's a count, right?
but there's no sample size of this. Or no, sorry, there's no sample size.
Yes. Therefore,
It's a T chart. C chart.
correct. And just copy this. And transpose. Do that. Here, that. This one is quite obvious. Multiple periods.
Right.
You have a control there. Too many complaints. And then you have,
Does that mean 2 little complaints?
I'm sorry?
Does that mean 2 little complaints?
That one there?
That's
Yeah.
too many on the opposite side.
Yeah. That's probably what you want to observe, right?
It's like, that's not a bad thing, right?
It's not bad
I mean,
to
it's
yeah.
statistically significant, but is it not necessarily indication? Could it get
Yeah, but you still have to investigate that and say maybe
Oh, maybe that could, yeah.
so that you can repeat that. Whatever you observed there, maybe you had good people on the front desk or whatever. Okay, good. What do you call this in baseball? Change up. The first 3 problems were bug control charts, but this is still a quality control issue, or it applies to has many practical applications. Right? So let's read what this problem is about, and I'll give you examples of where this kind of situation. A production process consists of a 3-step process. What is this?
You have the eraser selected, I think.
The what?
Yep. So click annotate again, and then on the left, I think you have the eraser selected on the left-hand
On the
side right here.
There it is. Okay.
I think it's like, you need to click the pen and icon. A few icons above.
No
Right there.
one.
There you go.
No, it should be. Right. Right. Let's see. Right. So you have a 3-step process. And each process there is a survival rate or scrap rate. One is a complement of the other. And we're talking about a scrap rate of 10% in the first step and 6% on the second step. The desired daily output is 450 units, good units, okay? So that will be here. The question is, how many units must be started to allow for loss due to scrap? As I said, one of the applications of this kind of scenario is in education. We recruit freshmen, say 1,000 freshmen, and we have right. That's right. We have retention rate, dropout rate. So if our target is to graduate 450 students,
Do we have to?
knowing that, and then maybe let's say this is a 3-year program, 10% of those that start will drop the first year. Of those that remain in the first year, 10% will drop on the third, 6% will drop on the second, and 6% additional drop in the third.
So is that a cumulative 22? Or is it?
Well, it's not, you don't add them.
It's 6% of the 10% that are lost.
Exactly.
Gotcha.
So the question is, if you were to graduate 450, how many students will we need to recruit?
565.9.
555. How did you get
565.
what?
565.9.
All right. How did you get that?
If you multiply those percentages, like so it's 90%, 9 times 90.
Okay, so you're looking at the yield rate, right?
What'd you say?
Yield rate.
rate. Yep.
Okay. So you're multiplying this, Lawson?
Yep.
Okay.
You'll get 0.79524.
Okay.
And then you would do your 450 over top of that percentage.
Okay.
That'll give you what you need to start with to
Okay.
get 450.
Good. Okay. Or another way of looking at this is you don't know what the starting point is, and you will your yield after the first year is 90. You know, those that remain in the first year, 96% will return. And of those that 94%. So it's the same thing here. That's what Lawson did. It's really like this. So 0.79524x is equal to 450. So divide this by 0.79524. 0.79524. You get that 566. So SOU needs to have a minimum of 567 freshmen to start if we were to graduate 450. Question?
So I guess I'm a little confused because there's 3 distinct steps, but they would all be
Phases.
joined together as one variable.
Well, there's only one variable, X.
Wouldn't there be A, B, and a C?
No, just
Different
one.
steps.
No, just one. Just X, the starting point.
I think I understand.
Yeah, because here's what you were saying is that of the whatever you start, 90% of those will survive the first year. And of those that survive the first year, or 9%, 0.94 will survive. So you're just multiplying this by that to say that the yield rate over a 3-year period is about 80% or 79.5%. Okay, so I said earlier that this is really a situation that is can be applied to a number of situations. The college recruiting is one. Can you think of any other? We have a series of,
I can think of a change to the system that would probably help things across the board. Switch to a semester school.
that could be one, but we don't know. I mean, that's,
For the sake of the art, I'm sure. I was gonna say leftover materials for construction zones.
leftover.
Because obviously it has to be pooled into like a reserve area. I just know that with each was job to job sort of specifications, not all ores and materials specific to the actual job.
But then,
So there's like the percentage more or less would be the leftover materials, and then ultimately that would be compiled up into a separate account or category. But yeah, what I'm saying is, from the job to job or the process.
yeah, but it's a linear, as long as it's a linear process, in the end, you have this good units.
Right, that's one.
Okay, there's another one.
It's good for agriculture.
Yes. So, which
So anything for,
product in particular? Yeah. Product.
let's use marijuana, for example.
Okay.
So there's the harvest, and in that harvest, you're gonna have.
We're gonna start first with planting. How many trees you plant, right?
Yep.
And then not all of them will survive through the first whatever month or whatever.
There you go.
Okay, so yeah, in the end, you have a target of harvest of X number of pounds or tons or yeah. So yeah, that's a good example. Water treatment. How do you expand that?
So when a treatment plant, the Duff treatment plant, Smithford Water draws water from the Rogue River.
Okay.
It goes through a series of treatment processes.
Correct. Okay.
So sedimentation is one of the early processes where we remove all the dirt.
Okay.
But at the bottom of those basins, if you don't get that out, the basin just fills up with sediment.
Okay.
And it stops your treatment process. So you waste water to remove the solids that you removed from the water. And that goes into filtration.
Okay.
And your filters get plugged with what's left in the water. And you have to take your filtered water to backwash your filters to free up that particulate matter. So what you end up at the end of the process, and the clean water that you pump out to the system,
right,
is a percentage of the water that you started with.
Exactly. So it's a good another example. Anybody hear of fishes?
Fishes.
Fish.
Oh, sure.
How do they stop trout or?
Oh, but
lakes?
I mean, they're gonna lose whatever they're
That's
transporting
right.
or.
Yeah.
Sure.
How many rows they
How many
harvest?
Yeah.
Oh, and the what was that? Fish hatchery. Same concept applies. Yeah, but goal, you have to identify the death rate or the survival rate of each process, so you can determine how many salmon to. Okay, so there's many more applications of this. I've worked in book binding like this. Same thing applies. These pages are printed on what we call as a signature. They're like 11 by 17. Folded in, and you have to know exactly. You have various printing machines that lead into producing number of books, and in the process, there's scrap. So if you're going to produce 450, the client orders 450, and you were not accurate in your starting point. You started with too few. Going to happen.
You're not gonna have enough.
You have to reprint. And reprinting requires setup costs, right? If you have too much, well, the customer only ordered 450. Anything in excess, they don't pay. So understanding the behavior of your process is important. We good here? Any questions? Any examples you would want me to show?